Okay, let's go ahead and do an example of how you would calculate the acceleration of the Atwood machine if you were given the masses. So on the left we have 105 grams, and on the right we have 100 grams. If we press start, you see the acceleration. So notice both masses are accelerating at exactly the same rate because they are connected by a piece of string, right? So we're gonna calculate what that acceleration was, and then we're going to check the acceleration that was recorded by the vernier sensor on this velocity graph right here. So let's go to our calculation. So 105 and 100. So we're going to model our system. And again, the only external forces that are causing the system to accelerate are the gravitational forces. So we have Fg equal to mg. So we have 0.105 kilograms times 9.8 meters per second squared for mass 1. And then we have the same formula on the right for the gravitational force, but it's going to be 0.100 kilograms times 9.8 meters per second squared. Okay, sorry, I'm kind of jumping around there. So this one I can do in my head, and I get 0.98 kilogram meters per second squared, which is newtons. And then for the on the right, I need my calculator. I get 1.03 newtons. So G for 1.03 newtons, and that's that force right there. All right, so our equation is the sum of the forces should give us the mass times the acceleration of the system. Right? Don't forget this equation is for the entire system. Our forces are, well, first of all, the direction it's going to accelerate in is this direction right here, right? The direction of travel. So this force is positive, and let's use a different color. This force, whoa, forgot to draw it, right here, is opposite the direction of travel, so that's going to be a negative force. So let's go ahead and type that in. So we've got 1.03 newtons minus, or plus negative, 0.98 newtons. That's the sum of my forces. And my mass is going to be m1 plus m2. So 0.105 kilograms plus 0.100 kilograms. All right, that's the mass of the entire system. All right, so from here we can divide each side of the equation by 0.205 kilograms. And that makes this whole part of the term disappear because it's equal to 1. Numerator and denominator are the same. And 1 times A is A. On the left side, if we first calculate our numerator, we get 0.05 by subtracting 1.03 minus 0.98, so 0.05, and then divide by 0.205, we get 0.244. 0.244 newtons per kilogram, and that's going to be meters per second squared. So that is our acceleration of our system. All right. Now we're going to check our acceleration by analyzing the graph that was generated. All right. And I have that graph right here. Now the formula for acceleration, when you have constant acceleration, is simply change in velocity over change in time, right? To calculate that, you just need any 2 points along this graph, right? So in that case, it would just be like v final minus v initial divided by t final minus t initial. So I need 2 points, my final point and my initial point. So I'm going to use this point, which is 0, 0, right? So the first 0 is x and the second is y. So x is time. So this value is t initial, and this value on the y-axis is velocity, so that's v initial. All right, then I'm going to choose another point, and it doesn't really matter which point you use because it's a straight line. I'm going to use this one right here because that's where it crosses the graph. I'm going to go straight down, and I get 1 second. So this location, this point is 1.0, comma, that's my x value. And my y value is, looks like this little line right there, 0.24, right? If I follow across, that is 0.24. So 0.24 meters per second. So that is my final time, t final, and that right there is my final velocity, v final. So I'm just going to substitute into my equation, rise over run, so to speak, and v final was 0.24 minus 0, and that was meters per second. Those are my units for both of those. And then for time, my final time was 1 second, so 1.0, and my initial time was 0.0, and my units are seconds. So do the math there. 0.24 divided by 1 is going to give me 0.24. So I get 0.24 meters per second divided by second will give me meters per second squared. So 0.24 meters per second squared. And let's calculate or compare that to the value we predicted. .24. So very close. That's probably only off by about, I don't know, 2%. So the only reason why it's off at all, maybe because of, did we round somewhere? I did round a little bit, I think, when I wrote 1.03. Is that right? Let me double check that. 0.105 times 9.8. Yeah, I was running off a tiny bit. It was 1.029. So in any case, 0.24 versus 0.244. If you divide those two numbers, you get 0.98. So we're within 2% of the actual value.